Chapter 1.3 is real numbers and the number line. So to start this, we're going to get into the definition of sets and what sets are. So a set is just a collection of objects, and technically it's a collection of objects whose contents can be clearly determined, and the objects in a set are called elements of the set. So everything inside of a set is just called the elements of the set. So what we use to denote a set are going to be these braces, which I tend to call squiggly brackets a lot. So anytime you have those typically mean that you have a set of elements. So there's going to be two ways that we're representing a set. We're going to have the roster method and set builder notation. So roster method is pretty simple. Roster method is just listing the elements. So roster method, you literally just have the elements listed out, separated by commas. So here, if you remember the set of natural numbers, the set of natural numbers are just the set of numbers 1, 2, 3, 4, 5, 6, and so on. These are also called the counting numbers, because that's how we count things. So that's roster method, they're just listed out. And then you can put this ... which is called an ellipsis, meaning it continues in this fashion. So once the pattern is obvious, you just put the ellipsis there. Okay, so squiggly brackets around them, that means it's a set. That is roster method. For set builder notation, the elements are described but not listed. So it's a little different. So for example, we have it written down here. The way that we read this is first you see the squiggly brackets, so you know that it's a set. That first x, you start by reading it the set of all x values. And you don't really know what x is yet. The set of all x values, this vertical line is read as such that. And then you have this description to the right of it. So it's the set of all of x values such that, and then you read off the description. And the description here is x is a counting number less than 6. So you can see how it's described but not listed. So if we wanted this in roster method, the set of all counting numbers less than 6 would just be the natural numbers 1, 2, 3, 4, and 5. So remember, counting numbers are natural numbers, so that's how you would write it in roster method. They mean the same thing. So sometimes it'll be easier to represent a set using roster method. Other times it'll be easier using set builder notation. So let's get into the sets over here. So we already did natural numbers. So the set of natural numbers, we're going to be denoting that with an n. So a capital N, and we're going to be using that backbone, like the double lined for one of the parts of the letter. That represents the set of natural numbers. And we know that it's the set of numbers 1, 2, 3, 4, 5, 6, 7, and so on. Okay, so that one we should know by now. The next one is whole numbers. Whole numbers gets denoted with a W. So whole numbers is actually going to be all of the natural numbers as well as 0. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So what we would say is the natural numbers are a subset of the whole numbers because they're contained inside of them. Next one is going to be the integers, which we actually denote this with a Z. The integers are just positive and negative whole numbers. So I'm going to put an ellipsis to the left, meaning it continues to the left. So -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, and so on. So those are integers. Positive and negative whole numbers are integers. So once again, we can see that the whole numbers are contained in the set of integers. So we would say the whole numbers are a subset to the set of integers. And next one, rational numbers. So it's going to get a little bit more confusing here. So rational numbers, I'm going to use set builder notation for this one because you'll see in a second, you can't really list them off in roster method. So it's going to be the set of all numbers a divided by b such that a and b are integers. So all this means is that rational numbers, if they're not already written in this form, they can be. They're fractions where the numerator and denominator are integers. So let's see some examples here. So something like -5, that's a rational number because we can write it as -5 over 1. -5 is an integer and so is 1. Something like 2 over 3. 2 over 3, 2 and 3 are obviously both integers. If we wrote this as a decimal, this would be 0.6 repeating. So remember that little bar over the top means that 6 is just going to keep on repeating forever. So repeating decimals are actually rational numbers. Okay, and then something like 2 over 7. 2 over 7 is well, I won't do 2 over 7. I'll do 2 over 5. 2 over 5 is clearly a rational number because 2 and 5 are integers. As a decimal, this is 0.4. So you can see that integers are a subset of rational numbers. Repeating decimals are also rational numbers, and so are terminating decimals. So something like 0.4 is a terminating decimal because it stops. Okay, and then for irrational numbers, I'm going to denote that with a crappy capital cursive I. So an irrational number essentially is just something that is not a rational number. So it's anything that cannot be written as a ratio of two integers. So for jumping back to rational numbers real quick, you can probably maybe see where they get the word rational from. It has the word ratio in it. A ratio is essentially just a fraction, which is what a rational number is. So for an irrational number, it's not a rational number, meaning we can't write it as a ratio of two numbers that are integers. So another way to say this is a decimal representation. So it doesn't have to be a decimal, but if it is, if we represent it as a decimal, then the representation, a decimal representation that is not terminating nor repeating. So an irrational number, if we wrote it as a decimal, it would go on forever and ever, but it would never repeat itself. So examples of these, something like the square root of 2. So if we wrote the decimal representation for this, this would be about 1.4142135 6. It's going to keep on going forever and ever and ever, and it's never going to repeat itself. That is an irrational number. Square root of 3 would end up being irrational. Square root of 5, square root of 7. A lot of the square roots that are not perfect squares will end up being irrational. And another one that's pretty common is pi. So if you don't know pi yet, hopefully you know it after the next 2 seconds. It's about 3.1415292, and so on. So pi is a constant. It's always going to be this number. It goes on forever, and it never repeats itself, so it's irrational. So it's the number that it's used everywhere in math, but at the kind of the most basic level, it is the ratio between the circumference of a circle to its diameter. Okay, and then for the last thing here, we have real numbers. So real numbers get denoted with an R, capital R. So real numbers are pretty much every number you can think of except for imaginary numbers and except for infinities. The infinities are not real numbers. So what we could say here is, I'm going to use set builder notation. It's the set of all x values such that x is rational or irrational. So all rational and irrational numbers are real numbers. Okay, so let's do this example here. So let's say we have this set of numbers, -7, -3/4, 0, 0.6 repeating, radical 5, pi, 7.3, radical 81. So we want to write down all of the numbers that are in all of these sets that we just did. So for natural numbers, let's do that first. So let's list down the numbers from the set that are natural numbers. So remember, for natural numbers, those are all positive whole numbers, essentially. 1, 2, 3, 4, and so on. So the only number here that fits that property is radical 81, because that's actually equal to 9. So radical 81 is a natural number. Next, for whole numbers we know are going to be natural numbers, but also 0. This set does have a 0 in it, so 0 is a whole number. So is radical 81. Next, for integers. So integers are going to be, we also kind of can cheat a little bit and say that we know they're going to be all whole numbers, also including negative whole numbers, which in this case would be -7. Next, for rational numbers, so this is going to be any number that can be written as a ratio of two integers. So just going left to right, -7 is an integer. -3/4 works because because 3 and 4 are integers. 0 is a rational number because we can write it as 0/1 or 0 over anything. 0.6 repeating is a rational number because we said we can write that as 2/3 on the last page. Radical 5 is not rational. Pi is not rational. 7.3 is rational because it's a terminating decimal. And radical 81 is equal to 9, which is an integer, which is rational. And then for the last one here, for irrational numbers, we said, where'd they go? Radical 5 and pi were the only irrational numbers. If you typed in radical 5 into your calculator, you would see that it goes on forever. It doesn't repeat itself. And real numbers, all of these are going to be real numbers. So every single one of these numbers are real numbers. Okay, so brings us to our next thing with the number line. So the way that we can kind of graph numbers and plot down numbers is using a number line. So essentially it's like a one-dimensional graph. So you can see that we have just a line with numbers in order. We have 0 in the middle, and all the way to the right they are positive of 0, and to the left they are negative. So the more left we go, the more negative, the more right we go, the more positive, and numbers increase from left to right, as we can see. Okay, so let's do an example of this. It's pretty self-explanatory. So let's graph each rational number on the number line. So let's start with -3/2. So when you have an improper fraction, it may help you to change it to a mixed number to see where it actually is on the number line. -3/2 equals -1 1/2, which is -1.5. So think back to the first section or something that we did to convert to a mixed number. So -1.5 would be about right here. So this is -3/2. Next one for -2/3. -2/3, if you don't know off the top of your head, as a decimal would be 0.6 repeating, -0.6 repeating. So -0.6 repeating is a little bit smaller than 0.5. So that's going to be about right here. This is -2/3. And next for 0.5, 0.5 is just 1/2. So that's going to be right here. So that's 0.5. For 1 1/3, that's going to be 1.3 repeating. Or you go to 1 and then you go 1/3 of the distance between 1 and 2, which may be about right here. So next one, 23 over 8 might be a little bit harder. So let's actually go through and do that. So converting this to a mixed number. Oops, 23 over 8. 23 divided by 8. It goes in evenly twice. Multiply, subtract, we get 7. So 23 over 8 is going to be 2 and 7/8. So 2 and 7/8, that's almost all the way to 3, so about right here. And then for 3.25, that's going to be, hopefully that one's pretty easy right here. And then for the last one of 4, that's just directly on 4. Okay, so that's just an example of labeling some of those on a number line. And for one of the last things for this section is absolute value. So the absolute value of a real number is going to be denoted with the bars next to it, the vertical bars. It's the distance from 0 to x on the number line. So absolute value is a distance from 0. It's always going to be non-negative, meaning it's always going to either be 0 or positive. So the technical definition is denoted with this piecewise function. So a piecewise function, it essentially chops up a function into different parts based on the domain, which means based on what numbers we're referring to. So the absolute value of x, it's either going to equal negative x if x is negative. So that's what this first part means. It's equal to negative x if x is negative. If it's equal to negative x and x is negative, that makes it positive. So I know it looks confusing, but that's all it's doing is making the value positive. If x is greater than or equal to 0, it's equal to x itself. It's just equal to itself. So if it's positive, it just stays positive. So it looks confusing, but that's the technical definition. So when we're evaluating these, expressions, and we have an absolute value in there, evaluate what's inside of that first. Kind of treat it like a parentheses almost. So let's do some examples. So let's rewrite all of these without the absolute value bars. So the first one is the absolute value of 3. So all we have to do is make whatever's inside of there positive. It already is positive, so it's just equal to 3. So what it's technically saying is how far away is 3 from 0 on the number line? It's 3 units away, so the answer is 3. For an absolute value of negative 2, once again, you just make it positive, and it's a positive 2 when you drop the absolute value bars. But it's technically saying how far away is negative 2 from 0 on the number line? The answer would be 2. So it gets a little bit harder here. We have negative and then the absolute value of 5. So the absolute value of 5 here is going to equal positive 5. However, we have a negative in front, so it's negative 5 is our answer. So based on order of operations, this is like saying negative 1 times the absolute value of 5. Negative 1 times 5 is negative 5. Next one, negative absolute value of negative 7. The absolute value of negative 7 is positive 7, but once again we have the negative out front, so negative 7. Okay, just always remember to do the absolute value first, and then whatever's outside of it, do it after. Next one, for absolute value of 17 minus 23. So we have to do what's inside of it first. 17 minus 23 is negative 6. The absolute value of negative 6 is 6. Oops. Okay, and then for the next one, it's going to get a little bit more confusing here. We have the absolute value of 2 minus pi. So we don't want to approximate for pi. We don't want to, if we're doing that, then we're rounding. We don't want to round. We want an actual answer. So hopefully you guys can agree with me that 2 minus pi is going to be negative, because it's about 2 minus 3.14-ish. 2 minus that will give us a negative answer. So all we have to do in this case, in order to drop the absolute value bars to get a similar expression, is flip the order. So the absolute value of 2 minus pi is equal to pi minus 2. So if you have a difference between two values and it's negative, the absolute value of it, all you have to do is flip-flop the order. Next one, we have the absolute value of radical 3 minus 1. Radical 3 is going to be 1 point something. That's going to be positive, because 1 minus 1, something greater than 1 minus 1 will give us a positive answer. So all we have to do here is drop the absolute value bars, and that's it. So this will equal radical 3 minus 1, whatever that happens to be. Okay, next one, let's evaluate this expression for x equals negative 5. So we're going to plug in a negative 5 into x, just like we did previously in other sections. So we get negative 2 times the absolute value of 4 times negative 5, plus 10, and then plus 2. So we need to evaluate the inside of the absolute value bars first. So 4 times negative 5 is negative 20, so multiplication first. Negative 20 plus 10. So negative 20 plus 10 in those parentheses is going to give us negative 10. The absolute value of negative 10 is going to be positive 10. So that's going to be negative 2 times 10 plus 2. Negative 2 times 10, negative 20 plus 2. We get negative 18. Okay, and the last one here, a little messy, simplify. We have this huge fraction, so let's deal with the numerator and denominator separately. So looking at the numerator, we have an absolute value, so let's do that first. So 12 divided by 3 times 5. So inside of the absolute value, we have to do the exponents. 2 squared is 4. 3 squared is 9. Oops, absolute value. And in the denominator, we have 6 squared, which is 36. So the numerator, we have to finish the absolute value portion, so it's going to be 4 plus 9 is 13. Denominator, 7 plus 3 minus 36. So work left to right, 7 plus 3 is 10. So it's going to be 10 minus 36. Go up here. Numerator, I'm going to change I'll actually divide right now because we can see that we only have division and multiplication, so work left to right. 12 divided by 3 is 4. So 4 times the 5, the absolute value of 13 is just 13. Denominator, 10 minus 36 is negative 26. And in that numerator, 4 times 5 times 13, it doesn't matter the order in which we multiply. 4 times 5 is 20, times a 13 is going to give us 260. So 260 divided by negative 26 is going to be negative 10. So the whole thing simplifies to negative 10. Okay, so that is it for chapter 1.3.